Thank you, Ahmed, for highlighting the features of the TPA corrosion model and for showcasing the user experience from within PIPESIM. As you mentioned, it has been a long journey that has led to this milestone day, and I appreciate the patience and support of yourself and others on the PIPESIM leadership team, and also recognize the strong advocacy of the Canadian PIPESIM client services and software development teams who seeded the idea beginning in 2015 and who worked hard to make the integration of the TPA corrosion model a reality. This is the structure I will follow for the next 20 minutes as I explain the origin and the innovative technical elements included within the TPA corrosion model and how the model is designed to be used as the foundation of a quality integrity management program. We will continue with the introduction and a discussion of the motivation behind the TPA model, and will identify root causes of pipeline failures, share a brief overview of historical industry performance, summarize the benefits of the TPA corrosion model, compare and contrast the TPA model with traditional industry corrosion models, summarize the design basis of the TPA model within PIPESIM, review the 28-year history of the TPA model, including a summary of how the model has been validated over the years by comparison with actual inline inspection data. We will quickly review the top 5 reasons to perform a TPA project and showcase how the TPA model serves as a reliable technical foundation for a quality pipeline integrity management program. Before closing, we will quickly review 8 TPA case studies, followed by a summary of conclusions and final wrap-up. In 6 weeks, I will salute the 40th anniversary of my first day at Shell Canada. I was hired out of school to work as a pipeline integrity engineer, supporting field operations with the assessment of corrosion hazards and the design of proper mitigation monitoring and inspection plans. During those early years, I became motivated by a series of pipeline performance patterns that I noticed and which continue to persist today throughout the industry. Noticing these early patterns provided my motivation to create an advanced corrosion hazard assessment model that has evolved over 28 years to become the TPA corrosion model that sits within PIPESIM. One observation during my early years was that every corrosion event was a surprise to the organization, and that every corrosion event triggered substantial disruption and stress. I noticed that every pipeline that corroded or failed had a corrosion mitigation program applied, and that often a collection of corrosion coupons or real-time online corrosion monitoring stations were installed at a variety of points along the pipeline structure. I noticed that a pipeline with corrosion defects discovered from an inline inspection at the beginning of the pipeline failed at the end of the pipeline upon implementing a weekly pigging program, and that the failure site was at a location that did not show any corrosion defects when the line was inspected. In this situation, the pigging mechanically removed accumulated water containing corrosion inhibitor before the water could reach the downstream location. The pigging activity hindered effective mitigation. I noticed a pipeline with a monitoring station located at the end of the pipeline, but failed at the beginning of the pipeline, and a pipeline with a monitoring station at the beginning failed at the end. I noticed that corrosion occurred at locations very different than the locations where corrosion coupons or online corrosion monitoring stations, and that the monitoring devices rarely, not never, but perhaps never, but certainly rarely did they detect elevated corrosion damage, even on pipelines that failed. I noticed that the leadership team began to believe that corrosion monitoring was dangerous, as it provided a false sense of control where control did not exist. I noticed that corrosion damage always seemed different than the type of corrosion damage we expected from the transport of normal oil, water, and gas fluids. I noticed that severe isolated pitting corrosion dominated instead of the expected general wall loss corrosion mechanism. I noticed that corrosion rates occurred at rates substantially higher than those expected from the transport of normal fluids. Accelerated corrosion failure rates on high-consequence pipelines occurred within 54 days, 89 days, 120 days following commissioning, and these events caught the integrity and field teams completely off guard. As I continued to travel throughout dozens of well fields experiencing corrosion damage and repeated failures, it was obvious that traditional rules of thumb and simplified hazard models based upon pipeline diameter and superficial fluid velocities were not adequate for pinpointing where corrosion damage will occur, and nor were they able to pinpoint which pipeline was the most likely to be the next one to fail. So after 10 years on the job, it was clear the purpose of my career was to do whatever I could do to improve the industry corrosion hazard assessment models. And success of the corrosion model would be measured by delivering improved insight and guidance. So mitigation, monitoring, and inspection activities can be better optimized to the corrosion hazard profile. That is exactly what we have achieved by the development and implementation of the TPA Corrosion Model within PIPESIM. Let's take a look at the experience with field operations teams and what it created in terms of an understanding of root cause contributing factors leading to internal corrosion damage and failures. Then we can examine how the TPA Corrosion Model within PIPESIM has been intentionally created to solve these underlying factors. The underlying contributing factors that I noticed were common to all situations where internal corrosion damage was detected or where a pipeline failure occurred. Number one, the corrosive environment within the pipeline was not properly understood. The mitigation activities applied onto the pipeline were inappropriate for the corrosive environment. And number three, the monitoring and inspection program did not detect the damage prior to the failure event. To better accomplish my goal, I chose to enter the world of independent engineering consulting beginning in 1994. For the balance of the 1990s, our neocore engineering team made connections throughout the global subject matter experts in the field of pipeline modeling because we determined the pathway to improving corrosion hazard assessment models was to consider complex fluid flow data and the implication of water film transport properties as a predictor of potential corrosion activity. This is how I first became connected to the legacy teams and companies that now sit within the Schlumberger organization, and many of the same members over the years still remain active. We believed field ops teams deserve to have access to the insight provided by a combination of fluid flow data within a corrosion model as a means to fully understand the water film transport properties so they could have greater confidence that their mitigation and monitoring activities are more properly aligned to the corrosion hazard profile. To be successful, we had to create a corrosion model that placed the field ops teams into a predictive and proactive position, a position where they can forecast the implication of changing operating conditions and make appropriate adjustments to avoid initiating new corrosion damage and to stop the growth of pre-existing corrosion damage throughout all their pipeline systems. A look at industry performance. The experience and motivation for improvement to corrosion models is well aligned to the objectives and priorities of operating companies and regulators. In recent years, they both have realized that more must be done to improve pipeline safety, and with a prioritized focus on internal corrosion. They recognize that 20 years of onerous time-based regulations did not achieve the desired level of pipeline safety. Industry data over the past 20 years confirms that internal corrosion is the number one failure mode and that the failure frequency is on an increasing trend within all operating sectors. New performance-based rulemaking from PHMSA and the strategic plan published by the API AOPL organization places a priority focus on improving the understanding of internal corrosion mechanisms as a cornerstone to improving pipeline safety. The benefits of advanced corrosion models. Achieving proper alignment between the deployment of corrosion mitigation, monitoring, and inspection delivers rapid improvements to operational and financial performance. This graphic illustrates how an operating company with an industry-leading pipeline failure frequency rate, much higher than the industry average, has now achieved 30 months without a pipeline corrosion failure by adopting the TPA corrosion model, while dropping $6 million per year from the direct integrity budget. Traditional corrosion models. In all my years of taking part in NACE training schools, conferences, and technical committees, it has always been a situation that corrosion models imply corrosion rate models. As an industry, when we say corrosion models, we traditionally are suggesting corrosion rate models. The corrosion rate model, embedded into PIPESIM for the past 25 years, is the well-recognized NACE, DeWard, and Milliams model, which is completely logical and appropriate. The DeWard-NACE model is focused on proving a corrosion rate along the pipeline length with consideration of the partial pressure of CO2 and H2S, individual fluid velocities, the water chemistry, water holdup fraction, and operating temperature profiles. The NACE corrosion rate model supplies the worst-case pH profile and corresponding corrosion rate along the pipeline. As we notice from this graphic, the NACE corrosion rate model shows a decreasing rate as operating pressure and temperature decline along a pipeline, as expected. Also, we notice how the corrosion rate decreases as fluid velocities decrease, suggesting that the PVT behavior of the fluids, the kinetics of the reaction mechanisms tending to lower solution pH, are slower and slower moving fluids, and that an increase in fluid velocity results in more rapid reaction kinetics and a higher corrosion rate potential. In this graphic, we notice that the NACE corrosion rate is at its maximum at those locations where the water film is flowing at its maximum, and the corrosion rate is at its lowest in regions where water accumulates and moves slowly. The information provided by the NACE corrosion rate model, does not align whatsoever with the experience of actual real-world pipeline operations, and this is where the TPA corrosion model is designed to provide benefit. The TPA model design basis. Whether it is a production gathering, midstream, liquid, or gas transmission pipeline, the universal experience is that the most probable location for internal corrosion is where water and bacteria and solids accumulate, and not at locations where fluids are moving the most quickly. So this is the main goal of the TPA corrosion model, to supply an estimate of the real-world corrosion rate profile, but more importantly, to pinpoint the most probable locations for corrosion damage along a pipeline. This is a schematic for how the TPA corrosion model considers input from three-phase pipeline modeling in combination with the consideration of corrosion mechanisms to create a real-world corrosion rate and corrosion damage profile along a pipeline. There are many reasons why the TPA corrosion model delivers reliable results. Because application of the TPA corrosion model within PIPESIM prescribes the selection of a mechanistic three-phase flow correlation with preference for the OLGA-S correlation, characterization of the water film transport is rigorously developed. Also, because the TPA corrosion model combines deep subject matter knowledge and experience in the field of corrosion mechanisms, there are no technological barriers to the creation of a valid corrosion hazard profile, no matter the operating classification. Perhaps the only threat to achieving reliable results with the TPA corrosion model lies with the ability of the operating company and the user to properly define the physical pipeline network connectivity, historical, and present operating conditions. Noteworthy is how the specific information from the PIPESIM OLGA-S model is considered within the TPA corrosion model. Specifically, individual flow parameters are considered to create a water film velocity profile with consideration of the implications of H2S, oxygen ingress, bacteria, and/or debris to the overall corrosion rate and corrosion damage profile. The TPA corrosion model supplies an over-the-line corrosion rate compared to the NACE corrosion rate and identifies the most probable sites for isolated corrosion pity damage with an indication of the relative severity of the damage. 28-year history of the TPA model. I have explained how the TPA model has been under development since 1994, the result of 28 years of focused attention, adopting a machine learning approach based upon actual pipeline performance and failure events, and by considering the experience and observation of field operations clients on more than 250 projects in approximately 10 countries. Because of the success of our NeoCore engineering team throughout the 1990s, technical leaders in the field of internal corrosion summoned me to Washington, D.C. in 2002 to join a special industry technical committee focused on internal corrosion. The committee was organized by the American Gas Association and INGA in response to a series of high-consequence internal pipeline failure events on large-diameter gas transmission pipelines. The goal was to create an improved standard for the assessment of internal corrosion. The work resulted in the creation of the term Internal Corrosion Direct Assessment and the creation of a four-step ICDA project structure: pre-assessment, indirect examination, direct assessment, and post-assessment. The committee published the first ICDA standard method. It was for wet gas and normally dry gas pipeline systems, and it soon evolved into the NACE ICDA standard in 2005. The NACE ICDA standard is essentially a simplification of the complex modeling work that has evolved into the TPA corrosion model that now sits within PIPESIM. As the NACE ICDA simplified model gained acceptance, My consulting work continued to rely upon the full development of a hydraulic pipeline model as the feedstock into a corrosion assessment model, and this is the work that has evolved in its present form as the TPA Corrosion Model. The results of the TPA model integrate into the NACE ICDA 4-step project execution model by delivering a more reliable assessment of the corrosion damage regions along a pipeline. This is a project execution strategy that makes more sense than relying upon a simplified flow correlation for establishing integrity dig sites. This is a composite chart that compares the features of the TPA corrosion model with traditional industry models that rely upon a simplified NACE method. Essentially, the chart illustrates the value-added technical features and benefits the advanced corrosion model delivers to an operating company that chooses to adopt the TPA corrosion model within PIPESIM. The additional technical rigor provided by the TPA model delivers an enhanced characterization of the water film transport properties as the foundation of the corrosion hazard rate and corrosion damage profiles. This chart illustrates why the TPA delivers an industry-leading foundation from which to establish proper risk-optimized deployment of mitigation monitoring and inspection schedules and costs. The TPA corrosion model validation. The TPA corrosion model has been independently juried and confirmed as reliable by comparison of corrosion damage profiles versus inline inspection projects on over 150 projects since 1994 by regulatory agencies, global oil and gas production companies, and major pipeline operators. The comparison shows that 100% of critical defects greater than 50% wall loss have been predicted within a single pipeline joint by the TPA model, and 98% of all subcritical corrosion defects have been identified within 2 pipeline joints. Why perform a TPA corrosion model? There are at least 5 good reasons for completing a TPA corrosion model as the basis of an integrity management plan. There are equally good reasons for completing a TPA model for pipelines that have not been inspected as there are for pipelines that have been inspected. Number 1, to show the extent of internal corrosion damage along a pipeline with consideration of overlife operating conditions and with consideration of steady-state operations, upset conditions, potential ingress of fugitive debris, and non-conforming product quality. Number 2, to prioritize pipelines for inline inspection based upon the extent of expected corrosion damage. Risk-based scheduling of inline inspections avoids inspecting pristine, non-corroded pipelines and deploys limited resources appropriate to the corporate risk exposure. Number 3, when an inline inspection project shows internal corrosion damage, a TPA model provides an explanation of the factors that cause that damage. The TPA assessment positions field operations teams to implement effective mitigation programs that are highly likely to stop future growth of pre-existing damage and to eliminate failures and optimize direct mitigation costs. Number 4, as a tool for pinpointing the locations for effective corrosion monitoring stations. By placing monitoring at locations most likely to exhibit active corrosion, the field teams can be positioned to measure the effectiveness of their applied mitigation controls. By conducting corrosion monitoring at locations of maximum corrosion potential, the operator can cascade the monitoring results onto other pipelines that share a strong sibling association to the structure being monitored. Number 5 is to prioritize the locations for integrity digs as validation of integrity for non-piggable pipeline systems. Again, if the TPA model is used to classify a group of pipelines according to the likelihood of corrosion, the results of any direct examination on a single pipeline can be cascaded onto other pipelines sharing a strong sibling association. TPA with an quality integrity management plan. We are all aware there is a transformational shift occurring in the world of pipeline regulations, changing the definition of compliance. No longer does compliance be measured against alignment of activities to time-based regulations. The onus has shifted to the operating company as new rulemaking demands that operating companies, number 1, evaluate their integrity risk profiles, and number 2, conduct risk-appropriate mitigation monitoring and inspection programs to establish that their applied controls are effective. The new definition of compliance requires that integrity management programs increasingly rely upon complex internal corrosion models, such as the TPA model, to identify and respond to threats and risks that vary significantly across pipeline systems. The TPA Corrosion Model is a proven technical foundation for quality performance-based integrity management programs. Within it, performance-based integrity management program has consistently proven to rapidly deliver measurable improvements to pipeline safety, elimination of pipeline failures, with 40 to 60% reduction in direct integrity expense. The TPA Corrosion Model, case studies. I will briefly walk through a series of 8 images that highlights how the TPA model within PIPESIM has been used to add value within a corporate integrity management program for a variety of operating sectors. First, an example of how a predictive management of change integrity program has been implemented within a large regional sour gas gathering system. The changes in forecasted gas delivery rates were modeled within PIPESIM as a tool to forecast where and when changes to the corrosion mitigation schedules are necessary to achieve ongoing alignment to the risk of failure. Next, the use of the TPA corrosion model to properly align mitigation programs within an oil gathering network. The evaluation of the implication of oxygen and biomass debris into a solution gas pipeline system downstream of an oil battery. The implication of changing gas flow rates versus time downstream of an infield booster compressor station. The implication of changing gas rates versus time in a long wet gas midstream pipeline downstream of a major compressor station feeding a large regional gas processing plant. Evaluating the implications of a non-conforming wet gas and debris entering a high-pressure gas transmission pipeline. The implication of water and debris settling within a long NGL liquid transmission pipeline in a study to determine the integrity hazard profile variation responding to a change of NGL shipping rates. The implication of oil-water slippage and stagnant water accumulation in a long crude oil transmission pipeline with changes to oil delivery rates and with consideration of a debris and oxygen ingress as contributors to accelerated local corrosion damage. Prior to wrapping up the presentation, I will demonstrate how our TPA corrosion consulting services makes use of the results delivered from the TPA model within PIPESIM. By applying post-processing algorithms onto the output data from PIPESIM, we create a corrosion management dashboard designed for the use by integrity management and field ops teams. The TPA corrosion management dashboard provides a corrosion hazard profile and corresponding risk-optimized corrosion mitigation guidance charts for 10 different flow cases for multiple pipelines. The dashboard performs automatic post-processing of the PIPESIM TPA results to create an updated corrosion hazard and mitigation plan in response to manual entry of operating parameters that reflect local knowledge of the user. The parameters may include entry of oxygen ingress, bacteria, debris, picking frequency, methanol injection for gas pipelines, and whether the pipeline operates in intermittent service. The user can also define whether there is known pre-existing corrosion damage as determined by historical failures or from historical inline inspection results. Based upon the defined user entry values, the baseline PIPESIM TPA calculated results are processed to create an updated corrosion hazard profile and a risk-optimized mitigation guidance chart. Again, for the selected pipeline, the user can view a report that includes a chart of prioritized mitigation options from which the field ops teams can select the most appropriate option by consideration of their knowledge of the detailed system and their operating experience. Conclusion and wrap-up. In summary, I suggest that investing to learn as much as possible about what is happening inside an operating pipeline dramatically improves the chances of achieving long-term reliable performance. And as a final comment, delivering the results of every TPA project since 1994 has been a thoroughly enjoyable process of discovery for field ops and chemical teams as it reveals new insights that significantly enhance their ability to deliver reliable pipeline performance at the lowest cost. For those operating companies who have adopted PIPESIM and the TPA corrosion model as the foundation of their integrity management program, they wonder how they could be otherwise successful at delivering reliable performance. Finally, I express my appreciation to both John and Amit and to the entire PIPESIM team for their support they have shown to the TPA corrosion model. And I also appreciate the time the audience has invested to learn about the technical details of the TPA model and our vision for how the model can be integrated into a corporate integrity management program to deliver improved financial and operational performance. I'm excited now for the opportunity to field some questions from the audience, so I send it back to you, John. Thank you.